All right, good morning. We are pushing on through chapter 8 in our delightful book here. And we've got some really cool stuff to start to talk about here. We are going to be addressing the states of matter. And while some of it will no doubt be stuff that you're familiar with, there's also plenty of stuff that you may not have thought about. And certainly, as we go on into the chapter, you're going to see more stuff that maybe you haven't gotten all the way through thinking about, and so you're going to be super familiar to all of this. So I always kind of like that the best, where we know a little bit about something, have an idea of what we're talking about, and then we really get into the details of it and find out there's really a whole lot more there than we thought. All right, so without further ado, let's kind of dive in here. First, the stuff that you know already. We got solid, liquid, gas, plasma. Okay. Obviously, you've heard all those. You've had physical science. You were in second grade at some point, so not much more to say there. But guess what? That may show up on our Quizzus Magnissimus that we're having for Chapter 8. Okay, this is another chapter that really doesn't warrant a full quiz and test. So we're just going to have a large quiz, okay? What does that mean? That means if you guys have questions on your homework, if you have questions about stuff we cover in class, that means you need to let me know, okay, that you're confused about something, or you don't understand, or you missed it, I was mumbling, whatever. You couldn't read what I was writing. All those are definite possibilities, and no one's going to have their feelings hurt if you ask a question, okay? But that means that when we have our 50, 60-point quiz, that's going to be the first examination and the last examination for this chapter, okay? So, you know, put on your big boy pants or your big girl pants and email me and let me know if something's not clear. No one's going to bite your head off about it, okay? So maybe a way that you haven't thought about it, it says a little bit about vapor. I don't really care whether you use the word vapor or not. You know, the only thing I've really heard familiar in that is water vapor, because water is a liquid at the regular everyday temperatures, and it's only when we heat it above a normal temperature that it becomes a gas. And just in case you were a little bit confused about it, if you can see the jet of what looks like smoke coming out of a tea kettle or whatever, that's actually not steam. Steam is an invisible gas, and it's only once that has cooled off enough to change back into very small droplets of liquid water can you actually see it. So the smoky stuff is not steam, that is liquid water that is suspended in the air. The key point of this paragraph here, internal energy of a substance is what distinguishes the states from one another. Okay? Begin with a pure substance in a solid state, continuously heat it, transitions from one state to the next as the kinetic energy of its molecules gets higher and higher. Okay, so what did we talk about with the kinetic energy? Okay, that's what gives gases pressure. And this is the kinetic energy distribution. Remember, these have all got the same amounts of energy, but they've got different velocities. Okay, as those masses change from one to the other, the velocities get lower and lower. So xenon, which is 54, has an average velocity of 250, while helium, which is 2, is way over here, over 1,000. Okay, so remember, that's what we're talking about when we talk about the kinetic energy. And again, in our sensory way, we talk about that as temperature. Okay, but that's really a measure of the internal energy that's captured as kinetic energy. All right. Low internal energy means its temperature is low. If the energy is low enough, the substance will be in a solid state. Okay, clearly, again, we think of something that's transitioning all the time. We're going to go back and forth using water constantly as an example because it's, as we talked about in the Asimov stuff that we read, the thalassigen that we were calling it, it's one of the few substances that can exist at all three states in our everyday life. Okay, water vapor in the air is invisible, makes it humid. Liquid water, obviously what we drink, swim in, whatever. And then solid is frozen ice. Okay, so as we lower the temperature, we're robbing those atoms of kinetic energy. All right, and so we the key here is that they are then closely packed. Okay, and I think part of your homework is gonna be a little messing around with a computer simulation, just to get you guys kind of in the intuitive sense of what's going on in the different forms of matter. All right, so basically solids, they're pretty close together. Their intermolecular forces are high, and at the basic sense, a chunk of aluminum, which is a solid at room temperature, is no different than a chunk of ice. Just because we usually see something as liquid and becomes a solid doesn't mean there's something different about that solid. Okay, so all solids kind of share some of these characteristics in the fact that their molecules are very close together. All right, so interestingly and quickly, we have many molecular solids such as glass and plastics are amorphous. Okay, amorphous means without shape. Okay, and basically all that means is that instead of having a rigid crystalline structure like ice does or metals do or lots of ionic solids, the molecules are not actually locked together in a specific chemical bond. However, interestingly and incorrectly, he points out that amorphous solids such as glass can flow at an extremely slow rate over an extended period of time. This is actually not true at all. And I'm actually going to share an article for you guys to read so that you can see that. I'm going to make a note right here so that I can just say share glass flowing article. Okay, it actually gets into it. It's interesting. You guys can read it. Maybe there'll be a couple bonus questions about it, whatever. That's actually not true. There are plenty of things that are very, very slow-flowing liquids. I'll also send you a video about the pitch experiment, and it'll tell you a little bit about that. It's not a solid. It's just a very, very slow-flowing liquid. Very, very viscous is the word that we would use for that. So I'll let you guys check that out and learn a little bit more about that because that's just cool stuff and helps you think through some of the different things here. All right, and so the specific things that we want to note is that solids, what do they have? They have a definite shape. You set them on the counter, they don't change shape. Okay? And they have a definite volume. Okay? And while we're talking about them like this, let's talk about the other ones. Liquids. All right, and you need to know these. Okay? So if I'm writing them here, you need to be knowing them because you may or may not be asked about them. All right, so what do we know? We have no definite shape for liquids. You can pour them from one container to another, but they do have a definite volume. Okay? You got a balloon full of water. You cannot squish all that water down into a smaller volume. Okay? And what we call this is having the general principle of incompressibility. Cannot compress it. All right, now, just to be technically correct here, okay, and in physics we would talk more about this, but the bulk modulus, a weird name in my opinion, but who asked me, you know? The bulk modulus actually is the amount of compression that a solid or liquid experiences under a given amount of pressure. We talked a little bit about it when we did that metals and materials thing where we talked about brittle or tough or strong or whatever, right? So it's just that the forces have to be so large to compress something that in our everyday experience we would say that they are incompressible, okay? All right, and so, you know, you put 1,000,000 pounds on a steel beam and it's actually going to get shorter if it doesn't buckle, okay? It's going to get shorter. It's going to be squished. You're actually pushing those atoms closer together and it's taking up less space, okay? But, like I said, it's got to be like 1,000,000 pounds on one thing or whatever, okay? So it, for all intents and purposes, for our intents and purposes, and certainly compared to gases, liquids and solids are incompressible. Which brings us to gases. They have no definite shape, nor do they have a definite volume. Okay? So what does this mean? Put a solid in a container, it doesn't do anything. Okay? It doesn't change its shape, doesn't change its volume. You put a liquid in a container, it does change its shape, but it doesn't change its volume. Okay, I pour it from one container to the other. It's like one of those tests to figure out how mentally advanced a toddler is. Can they figure out that it's the same in this one versus that one? Okay, you pour it from one container to the other, there's no change in volume. Gases, however, they change their shape and their volume, and they fill a container. Okay? And what does that mean? It means they are... All right, we're done with this, so I'm crossing out. It's still right, we're just done talking about it. So they are compressible. Okay, so let's think about this. I've got a cylinder. Okay, and I've got a piston that goes into that cylinder. Okay. And it's got like a little rod on it that we can push down in it. Okay. And let's say I've got 10 grams of gas in here. Where is that gas? That gas is all through here. It's everywhere. It's filling that container. Okay? It's everywhere. Now, if I have that same container, all right, and I push that piston down to where it's right here. I'll make this one longer so my little rod stays the same length. Okay, guess what? I've still got 10 grams of gas, and it's still filling the whole container. That's just an accident. That guy did not escape. We would never let that happen. All right, 10 grams of gas. He's still in there, but it's now all squished down. Okay, so the density has changed, but it's still filling the container. Which means a change in that volume, and it doesn't have a definite shape because its shape has actually changed as well. Okay, you could not do this with water, not in any significant way. Okay, you fill a thing with water, make a watertight seal right there, and try and press it down. Good luck. You're not making it go anywhere because water is incompressible. It's incompressible. Okay, all right. Need to know this. I'm not sure how that may be asked, but this is a simple enough concept. I may ask you in a slightly creative way that makes you actually think through and compare and write and answer carefully. Okay. So, all right. All right. So what does that mean? We've covered solids and we've talked about liquids and their characteristics. Okay. And so we have added some energy from solid to liquid. Okay. That is often well, we haven't talked about pressure yet and how that affects that, and we'll see how another way we can make what's called a phase transition, a transition from one phase to another by using pressure. But typically, assuming we hold pressure constant, okay, to get something to go from a solid to a liquid, and again, think about ice melting. What's happening there? That ice has a certain amount of internal heat that is then added to as it as heat moves from, let's say I put a piece of ice on the countertop here. That countertop is above freezing. Okay, it'd be very unpleasant if it was freezing. All right, so let's say it's 20 degrees Celsius. Well, that ice came out of the freezer at 0 degrees Celsius. I put it down here, and that 20 degrees worth of heat, we'll talk about specific heat as we move into the next couple of chapters, that heat starts moving into the ice, okay? And it's raising the temperature or the kinetic energy of the average atom of ice until that molecule starts to move around enough that if they're solid, they're like this, okay? And if they're liquid, they kind of become like, you know, a 9-year-old boy, and they're just kind of vibrating all over the place. And if they get too close, they're going to bang into one another, and they kind of bounce, and they get further away, and they come back together, and they bounce again, okay? In the little simulation, you're going to see the difference in those, okay? And it's going to help you internalize that, okay? So, but that movement is temperature, that is heat, okay? And so as they move apart, they lose their crystal structure, and they become amorphous. They lose their shape. Okay, they no longer are rigidly locked together. They lose their shape and they relax and they go into a liquid. Okay, and that's actually what's happening there. Okay, that energy is overcoming those bonds. Remember how we talked about to break bonds, you've got to put energy into something. Well, that's literally what's happening. That energy is going into these bonds and finally overcoming them. Okay. And so we've talked a little bit about hydrogen bonding and how that can hold liquids in their liquid state. We talked about that in the Asimov stuff. And so I think you guys are pretty familiar with that, but just kind of try to reach back into your memory if you can and draw that forward and link that to what's going on here. Okay? Okay. Let's see. What else? All right, that's all I wanted to talk about there. Talk a little bit about surface tension. It's a super interesting topic. Just don't have a whole lot of time to go into it, but basically it's kind of, you know, these forces between, especially things like water that have high intermolecular forces, they're a lot more attracted to other liquids than they are to the gas above them, okay? So that causes them to be attracted here, causing them to want to stick to one another, which is what we experience as surface tension, okay? And that's right here. All right, capillary action is actually the opposite, where molecules are more attracted to something outside of the liquid surface than they are one another. And see what's actually happening here. This is the surface of the water, and that water is being drawn up the side because it's more attracted to the glass than it is to the other water molecules. Okay, capillary action is what we experience in a paper towel. As it, you put it on the thing, all the water goes right up into that. It's capillary action. It's more attracted to the cotton fibers or whatever they make that out of, tree fibers, paper fibers, than it is the other water ones. Okay? Diffusion, a tendency for molecules spontaneously to mix and mingle. Liquids and gases. He makes a little note here. Apparently it happens in solids too, which is pretty cool. I did not know that at all. Foreign atoms such as carbon atoms in an iron lattice of steel alloys migrate through the lattice. I'd be interested to see how that happens. I haven't read that before. That's really cool. Diffusion, you can see that if you've ever done food coloring. Again, it's not something that's super new for you, but what's actually happening is that these random movements of the water molecules essentially self-stir that mixture until it's completely evenly distributed. And all of that has to do with maximizing the entropy or the disorder of the whole system there. And you can read about all that. Lots of processes. We're certainly going to talk about that more in detail as we talk about a lot of reactions and do they go on their own or they need to be helped? Are they spontaneous or not? Kind of like the the metal activity series. Is this going to happen on its own? We look at a table and see that it's a little bit like that, a little bit more complicated, but essentially the same thing. This is a situation where it goes from this to this, and it maximizes entropy. And it will never go from this to this, because that would be losing entropy, which never decreases in the universe. And so just store that away for when we talk about that another day. All right, finally, there are four. Next, we come to gases, which are like liquids in some ways, right? Like they don't have a definite shape. So a liquid's almost sort of a half solid, half gas. It doesn't have a definite shape. It's able to move around enough to do that. But it does get stuck in a definite volume. They're stuck together at a certain distance from one another, and that's it. Well, if we keep pouring energy into there, we can overcome that. And those molecules actually break loose, and they have enough kinetic energy that when they collide, they don't stick together anymore. They just bounce. And we talked about that in a perfectly elastic collision. If it comes in at 10 meters a second, another one leaves at 10 meters a second, or he leaves at 10 meters a second, okay? None of the kinetic energy is ever lost. It's a perfectly elastic collision. Okay, and obviously this is just a representation. He says, the sizes are way off here, but it gives you the point. Okay, they're not hanging out. They're randomly running into one another, but they are not stuck together in the way that liquids are. Okay, it's interesting to note molecules in a gas diffuse faster. Why is that? Well, because everything's moving a lot more quickly in gases. Okay, so their velocities are much, much higher than they are in a liquid. You can see this takes an hour. If you dropped one vapor in here and there was another vapor in there, they'd be mixed within a matter of minutes or less. Okay, we talked about gases being compressible, and we'll talk more about that. All right, finally we come to plasmas, something about which I am not super knowledgeable. So we just need to know, first of all, we need to know a plasma is an ionized gas. Okay, what does that mean, ionized? What does it? Remember, it has to do with electrons, and they're being ripped free, basically, of their atoms. So they are no longer attached to the atom they came with. Okay, so they're kind of free floating, and in some ways, this mimics metals. Okay, and we'll talk about that in just a second. Energy. Let's see. The O2 and N molecules, we're talking about a lightning strike right here. O2 and N molecules are ripped apart, and atoms of nitrogen and oxygen are ionized to produce a plasma. Okay, I thought this was really cool. The bright violet glow of a lightning strike is similar in color to the light emitted by the nitrogen gas tube right here, because it's primarily nitrogen in our air. I had no idea about that. I thought that was really cool. Okay, so we got to put a lot of energy in it to do that, right? So we talked about how much energy it takes to ionize a single atom, 15 chapters ago, 100 years ago. But now we're talking about ionizing a whole band of atoms, of millions and billions. So where does that come from? It can be supplied by intense heat, okay, or by high voltage electricity. I'm sure there are other ways. So what happens is, as you do that, as you create this plasma area, this ionized band of air, the results of gas is a gas of ions, electrons, protons, and neutrons, like all hanging out, all kind of not being in their normal state that they are. Okay? The key here is that plasmas conduct electricity and are affected by magnetic fields. Okay, and it applies that to the aurora borealis, which is cool. So how's this like metals? Well, we've got these free-floating electrons, just like the electrons in a metal. And so if you're sort of recreating this electronic pool that this electricity can flow through very easily. Okay? So just kind of make those connections. Let's see. Ionizing radiation. Okay. Now, I'm already at 26 minutes, so let's push on through fairly quickly here. Phase transitions, phase diagrams. This is where interesting stuff we really start to talk about, and this is what your homework is going to be on to really dive into some of this. And so, what do we need to know about phase diagrams? Let me get you a little bit closer here. Don't want you to miss any of this. All right, so what do we have going on here? So this is a phase diagram, and like all graphs, it is simply a graphic representation of some information, and it's kind of presented in a way to help us make sense of it, as well as to maybe quickly reference it. So there are tons of phase diagrams for all sorts of compounds, all sorts of mixtures, all sorts of elements. Like say magnesium. What would its phase diagram look like? Okay, we'd need to know. We need to do experiments. And so what people have done over the years, they've done tons of experiments because these sorts of things are super useful for industry, for different industrial processes. You need to know exactly what kind of pressure and temperature affects things certain ways. So, but this is always going to kind of be a similar type of graph. And once we talk about that, I've got some examples of other ones. You can see how they're different and similar in different ways. All right, so some things we need to get clear in our minds here. All right, so we need to know everything that's got a number on here is noteworthy. Okay, so what do we have? We've got a couple of notes. Atmospheric pressure. Okay, that's 101.3 kPa, kilopascals. Okay, your homework's going to go over that a little bit more, but that's just we just call that what it happens to be on Earth, right? There's nothing special about that. You can see it's this kind of odd number. It's not like 0.00. It's just atmospheric pressure. It's what happens to be here. Okay, that's this line coming across. All right, note that this is your pressure axis. Every time we see a graph, you immediately want to look and see what each axis is labeled with, so that you know right off the bat, and that comes in on the ACT very strongly. And if you guys come to the ACT thing, we'll talk about that pretty in depth. You want to look at your axes really quickly, temperature and pressure. Okay, and this temperature is increasing this way and pressure is increasing that way, just like a regular graph would in algebra. Okay, so what we have are the different phases that an item, be it a compound, be it an element, be it whatever, can exist in. All right, so what are those? Solid, liquid, and gas. And we have these lines that separate them. Okay, you know that you got an ice cube, it's melting, but each individual atom is either a solid or a liquid. Okay, you might have a partially melted ice cube there in a puddle of water, and that amount of water is transitioning from a solid to a liquid. But at any given point, eventually, if you hold the temperature and the pressure steady, eventually it will either be all liquid or all solid. Okay, unless you are exactly on this line. Okay, so for example, at atmospheric pressure, I think, hold on, there may actually be the water lines over here. All right, so let's look right here. We'll just talk about water specifically. At atmospheric pressure, and note this is in atmospheres right here, and at 0 degrees C, we are on that line. That means if you have a glass of ice that's exactly at 0 degrees C, it will become eventually this sort of mixture of ice and water, and it's going to be sort of at a medium state between those, some ice and some water. Any warmer, it all becomes water. Any colder, it all becomes ice. Okay? So at 0.000 degrees Celsius, that's what it's doing. All right? So these lines are the boundaries between between solids and liquids, or between phases, excuse me. All right? And so then we've got another thing that's called the triple point, which is number 4 right here, triple point. You can see why it's called a triple point, triple being 3. You've got solid, liquid, and vapor. All are able to exist at that temperature and that pressure only. Okay? Let's think about it. If we're at that triple point, let's say we increase the temperature. At any given pressure and any given temperature, it can either only be solid or liquid. Okay, we keep the pressure here, we change the temperature, it can be solid, liquid, or vapor, but it can't be solid, liquid, and vapor all at once. Around here, it could be solid or liquid. Around here, it could be liquid or vapor, but there won't be any solid over here. There won't be any vapor or gas over here. Okay, only here do those 3 lines come together. So that's the triple point. You need to know that for sure. Okay, you need to know that, of course, this is called a phase diagram. This is going to be a pretty vocab heavy chapter. Okay, sorry for that. It's not my favorite, but it is what it is. Okay, so triple point, and I'm trying to find where that actual, there it is. Okay, point 4, it's called the triple point. Okay. All right. Other things to note. You need to be familiar with all of this. I hope you already are, so that it's a super easy check mark. Fill it out, no problem. Don't even need to study. You have various, if you're going from solid to liquid, we have melting and freezing as you're going from one to the other. Okay. If we're going from liquid to gas, you've got boiling in one direction and condensation in the other. I trust we don't have to talk a whole lot about that, but pause me and feel free to talk to that with Miss Barron if you would like, or if the class is confused. But then we have the less well-known, and this is obviously where you're going to have to refresh your memory. You have gas straight to a solid, which is called deposition. And note that that can really only happen at pretty low temperatures and pretty low pressures. Okay, that's typically going to be the case. Room temperature, not going to get a lot of things that deposit directly or have deposition happening. Okay, sublimation is straight from a solid into a gas, And obviously the most familiar one of that is dry ice or solid CO2, which sublimes directly to gas CO2, making it the perfect thing to ship ice cream or transplant stuff, because it doesn't turn into liquid and soak all your stuff. It just donates its cold or absorbs heat from its surroundings and becomes a gas, and then just escapes from the container. Okay, so it's super useful that way. That's sublimation. Okay, so you need to know all of these and be able to locate them on here, as well as just kind of explain maybe on a triangle with the 3 phases on it, which one is which, and draw that. Okay. All right, so let's just apply this just a little bit. Down there, about halfway down the page, talks about a pressure cooker. All right, and so let's think through what this means. Let's go straight over to our water one here. Okay, just to put some real numbers on it. All right, let's say we live at 1 atmosphere right here. Okay, which we're a pretty low state, so we live around there. Okay, what is the boiling point of water at this pressure? So what we need to do is we need to follow this line across and see where does that liquid become a gas. Boom. Oh, look, it's 100 degrees C. We knew that. Okay, where does it freeze? All right, it goes from liquid to a solid at 1 atmosphere. Boom, 0 degrees Celsius. Okay, we've got a triple point that's at a much lower pressure, but a slightly higher temperature. And that's where solid, liquid, and vapor gas can all, vapor water can all coexist in the same container, same area, same location. Okay? All right, so very quickly, let's talk about the critical point right here. And this is the critical pressure and critical temperature meet right there. Okay? And that critical point is the lowest pressure and the lowest temperature at which the liquid stops existing in its normal state. So, to be honest, I'm not exactly sure what this looks like or what properties change, but you just need to know that above that, it's a supercritical fluid which has no clear boundary between the liquid and the vapor. Okay, remember we talked about, so like you can see liquid water. Okay, you can't see water vapor. And when it transitions from one to the other, when that steam cools off enough to be a visible cloud, that's a clear transition from vapor to liquid. You're seeing it. That's not the case over here. Okay, it looks like something entirely different. Very high pressures, very high temperatures are what usually are required to make this happen. All right, so very briefly, I want you guys to be aware that other things exist here, other types of phase diagrams. All right, I thought these were really nifty. All right, so what do we have here? Oh, I need to move you guys up a little bit. All right, so here's carbon. This is fantastic. I've never actually seen a phase diagram of carbon before. All right, so what do we have? Solid 2, metallic, different than either diamonds or graphite. You know, graphite in your pencil is just a form of carbon. And so note that at fairly low pressures, although not super low, because look at how high we are. We're at an atmosphere, so 200 atmospheres and below. It's basically graphite all the way until you get super hot and then it turns into a gas. All right. So if you jack the pressure up, turns out you can turn things into diamonds. Literally coal into diamonds. I mean, like, that's not a joke. That's a real deal. But note how high the pressure has to be, and really kind of how the temperature has to go up too. So all in here is diamonds, super high temperature, higher pressures. You can actually get liquid carbon. No idea what that actually looks like. I'd be interested to know. Often these things are either glowing or, you just can't even see them because they don't react. They would basically they'd just be glowing, or they'd be smoking, or they'd just really difficult to actually get a look at what they would look like in a regular setting because they are so hot or under such high pressure. And then eventually you end up with this other state up here. And I guess the point of this is to look and see how different these things can be for individual items, okay, individual elements or compounds. Okay, let's look at carbon dioxide. Okay, we just looked at water. Okay, and look all the way up to this, at high pressure. Here's our one pressure here. From at 78.5, it's sublimed straight from. Look how high that pressure is that has to even create liquid CO2. So anything below 5 atmospheres, there is no way to get liquid. So it goes straight from solid to gas. Because when we're down at 1 atmosphere, it's only moving in this direction as the temperature changes. Okay? There's nothing else you can do. All right? And then we come over here. Let's look at helium. Okay? Look at our scale on this guy. Kelvin. Okay? Right here, absolute 0. Up to 5 Kelvin. So way, way cold. And it goes straight from liquid into a gas. You can't even get it to form a solid. Even at absolute 0, it's still a liquid because of weird things going on with the electrons and how they interact. It becomes a superconducting fluid, which is super weird. And if we have time at the end of the year, maybe we can cover some of that stuff. But you have to get up to 25 atmospheres at less than 1 degree Kelvin for it to even think about being a solid. Okay? And it just doesn't have any intermolecular forces. I mean, that's the deal. It just doesn't hold together. Okay? It boils at 4K. Okay, and to go from liquid 1 to here, I guess he's saying at a particular pressure, Anyway, so all that to say, things can look pretty different as far as individual phase diagrams, but they're all read the same way. You're graphing pressure versus temperature. Okay, so with that, I think that's gonna be about. Oh, very quickly, I want to talk about a pressure cooker. So what are you doing with a pressure cooker? All right, so let's look at this. If you've got pressure here, and let's say you're at 100 C, that's where water's boiling. Okay, until all of that water boils away and becomes vapor, you cannot raise the temperature any higher. Okay, you're saying, hey, I want to cook things faster. Let's get this temperature up. Well, what do you need to do? You need to be able to take that temperature all the way up to, say, 150 degrees, which would be kind of right here. Well, what do you need to do if you want it to boil at 150 degrees? Well, you come 150, follow that line up to here, and then come across, and you see that your pressure probably needs to be, now of course, like he says, these are not drawn to scale, and you're going to see an actual scale one in your homework, but excuse me, much above that pressure is where you would have it to boil at a higher temperature. Okay, so that's what a pressure cooker does. It allows that pressure to condense. And an Instapot, if any of your parents have one of those, that's what it's doing. It uses that water turning into gas to increase the pressure inside that area, and then that lets the water be much, much hotter in there because it doesn't dump over into gas. Okay, we're going to talk a lot about heat capacity, heat diffusion, heat of vaporization, works and problems next time. Okay, but as we increase the pressure, the point is you need to know that temperature that things make phase transitions. Typically, particularly, definitely in water, it goes up, okay? Until you reach a certain point with that critical point where you can't do that anymore and things get weird. But that's really hot, okay? That's really hot, and generally pretty high pressure. So even if you get really hot, it just becomes a really hot vapor until you get those pressures very high. So you can make steam very, very hot before it acts not like steam anymore. So interesting thing to kind of just think about. All right, so you'll have phase diagram homework. I will share the glass flowing article to y'all and the pitch experiment, so you can check that out. This is a really cool experiment in how viscous something can get before it really looks like it's a solid and acts like it's a solid, even though it's not a solid. And I'll share you the glass flowing article just to not to point out that he's wrong in here, but really just so, as I'm sure you guys have heard that. I heard that my whole life, and I thought it wasn't true. I looked it up. Oh, one other thing here. Take a note that ammonia has a particular characteristic that makes it a really good refrigerant, which means you can use it in big chillers to cool things off. So we visited the U.S. Foods, which is in South Flowood, and they have refrigerated lockers the size of Highlands Baptist. I mean, like, they're enormous. You walk in there and it's 100 degrees outside. You're sweating your tail off, and all of a sudden, within 30 seconds, you're shivering because it's 10 below zero in there. And you're like, oh, I'll be fine. You're actually not fine. You have about 30 seconds to get out of there before you get really, really cold. But those chillers at U.S. Foods they have a whole closed ammonia system. And it's more efficient because of the particular triple point and critical pressures and temperatures of ammonia that this, like we said, this looks different for all sorts of different things. Well, ammonia's is particularly suited to doing that. And so that's what they use. They don't use Freon. They don't use water or anything like that. They use ammonia to transfer that coldness, or really to pump the heat out of there to do that. So anyway, all right, sounds good. I've talked enough. Have a great day, and I will send you your homework.